This is a tutorial for conducting power analyses on ANOVA style designs. So, the first thing you have to do is install and load the package called Superpower. Make sure you have internet for this step. Once the package is loaded, you have to define a set of parameters for your analysis. The first thing you need to define is what kind of ANOVA design you're using. For example, in this example, we have a 2x2 within subject's ANOVA, so we define a parameter called 2W asterisk 2W, as seen here in line 10. If your ANOVA style design is different, for instance, if you have a 3-level ANOVA or a 3-factor ANOVA, then you can say 2W asterisk 2W asterisk 2W, and you can change the W to a B to change it to a between participant design. Once you define that, you define the alpha level, which is the p-value that's considered significant. That's usually set to 0.05, so you probably don't want to change it. Then you say the number of simulations that you want to run. More simulations produces a more stable result, but might take longer for your computer to run. The code here also gives us observed power and effect size for a given number of participants. So here I've set n to 20, but we're going to generate power curves later, so actually this number doesn't really matter. Okay, and now we're going to define some parameters about our underlying data. First, the standard deviation for each group mean. So here we're setting it to 30 arbitrary units. We have here the correlation between levels of a repeated factor. A lower R value is more conservative because you're assuming that less variance will be captured by the within participant nature of the design. By contrast, if the R value is higher, you're saying that the levels of repeated factors are more correlated across each other, thus capturing more variance. What I would recommend doing is setting this to a low value like 0.1 so that your power analysis is more conservative. Note that this number ranges from a minimum of 0 to a maximum of 1. Now we're going to give the names for the factors and the levels within each of the factors. So in this design we have stress and context being manipulated. So I have the factor stress labeled with levels stress 1 and stress 2, and the factor context labeled with context 1 and context 2. And now probably the most important step is to define what the means are for each of these conditions. So this follows the same order as the label names you'd given above. So for instance here I'm coming up with a list with means 10, 20, 10, and 50. Once you define that, you can visualize what the results look like. So for instance here you can see the means and standard deviations for each of the groups. So this is the data that we're actually simulating. Notice that we're simulating a main effect of context 2 because the numbers are higher for context 2, and also an interaction because for stress 2 only the effect of going from context 1 to context 2 is really big versus that effect is smaller at stress 1. Okay, so now this here gives us the numbers for our observed number of participants. So for instance, with 20 participants for these data, we have a 67% chance of capturing the significant effect for the factor stress, 96% chance of capturing a significant effect for context, and a 58% chance of capturing a significant interaction. Here you can see the effect sizes for each of those. And down here you can even get the power for t-test pairwise comparisons between the different groups. Recall that a good power is considered 80, so 80% chance of capturing a significant effect. Now the most important part of this power analysis is the power curve. So when you run this, notice that we're setting the minimum number of participants to test at 10, the maximum number of participants to test at 60, and this generates a power curve as seen here in the plot on the bottom right. So what this is saying is that for you to be able to detect an effect of stress at 90% of the time, then you need 40 participants. By contrast, to detect a significant effective context 90% of the time, you need 16 participants. Of course, if you're using a lower power threshold, in other words, a lower beta value, then you can just see, for instance, what you need to get 80 participants, roughly here. So for instance, for 80, you would need roughly 30 participants, given these data, to detect a significant effect of stress. Okay. And now in the code, I can just show you how you can rerun the code again easily, but simply just changing the hypothesized group means. So for instance, now we'll have a weaker effect. Notice how now the differences between context 1 and context 2 are smaller, and the interaction 2 is correspondingly smaller. So you can run everything as before. You have the same saved values, and now we can get the power results when we have this weaker effect. So here you can see that we need more participants than before. 57 to get 90% chance of detecting an effect. So this code can be very easily adapted for different hypothesized means and standard deviations, and you can also add or manipulate the factors for different ANOVA designs.